So this is a very recent advance in understanding gravity. In the morning, there was a talk by Dr. Satish, and he talked about Einstein's gravity. So I think I can skip most of the things in describing Einstein's gravity theory. Only one point that I have to highlight is that the conflict between Newtonian theory of gravity is with the special theory of relativity. Right? Newtonian theory of gravity advocates for an infinite propagation of the influence. On the other hand, special theory is very strict about the propagation speed. There is an ultimatum, light velocity, and that is not. These two are conflicting each other. So somehow we have to combine the theory of gravity with the special theory of relativity, and that's what Einstein did. If you combine special theory of relativity and Newtonian theory of gravity, what we may be often called as the principle of equivalence, that is already described by Satish, and you will see that gravity is curvature. So this is somewhat a very important point that is to be understood, but in order to explain it, it need even in the morning, it needs a lot of times. So we just taken it as granted that in Newtonian theory of gravity, gravity is a force between massive particles, right? And on the other hand, on the other hand, in Einstein's theory of gravity, there is no such force. Gravity means curvature in the space-time caused by matter or energy. This is the essential difference. Newton's theory advocating that gravity is a force. On the other hand, Einstein's theory telling us that there is no such a force between massive particles. Instead, gravity means the curvature on the space-time, and that curvature is produced by matter or say equivalently energy. This is the concept. And it made a remarkable predictions. I am skipping all this. This is what actually Satish has explained in the morning. So I am skipping that also. This is the equation. That also I hope whether you understood or not. Okay. So the theory was very remarkable. It predicts the bending of light. It predicts exotic objects like black holes, and it explains the expansion of the universe, and it predicts gravitational waves. So predictions one after another was verified, right? So it was an excellent theory, right? Maybe you can say that most beautiful and elegant theory ever created by a human being, right? But you know, everything is.
Why is it so?
Pardon me?
Why is it so?
Why is it so means what?
You said, of course, it is the same opinion is shared by several others.
Yeah.
But I fail to understand why it is considered the most beautiful theory or equation.
No, it's a subjective statement. Right? It is said by Landau in his textbooks.
Mathematically, I think both sides of the equation take the divergence 0.
Yes.
That's a geometrical property.
Yes.
Even matter is part of geometry.
Okay.
This is a view shared by, I forget his name, a great astronomer and theoretician who lived in England. I forget his name.
Eddington, you mean?
Eddington.
Now the beauty of the theory is that it relates, right, gravity with the geometry of the space-time. That's the thing.
Same correct. Yes. There is only geometry.
Yeah. There was no such theory before. relating, you giving an ontological status to the space-time and relating a...
Perfectly mathematical because the divergence is zero, both sides.
No, every theories are mathematical.
It is
They are making predictions on physical...
Yeah, that is the wonder. It's a miracle.
That's right. So I want to say that nothing is perfect, right? Even it is a very celebrated theory, there may be some elements of, what I have to say, drawbacks.
Mathematics is perfect. That's,
Even mathematics is not. That is what I want to share. So this theory is also having some very strong challenges. Even though it makes very remarkable predictions and bagged many Nobel Prizes, even though Einstein couldn't get the Nobel Prize for that theory. But the theory is, one has to say that it is not a complete understanding of gravity. Now why we are saying that, right? So as of now we understand gravity as the curvature of the space-time. If somebody says that, actually if you are claiming that gravity is not actually the curvature of space-time, then why you are saying that? What is wrong in Einstein's theory? The very first drawback of Einstein's theory is that, see, immediately after Einstein's put forward this theory, as mentioned by Satish, Hilbert proposed a Lagrangian, and you can create an action principle, and you can vary the action principle and create the equation of motion. That is Einstein's equation of motion. But there is an issue. And the issue is that, see, in the Lagrangian proposed by Hilbert, if you add a constant, right? We already know that if a constant is to be added with the Lagrangian, then the equation of motion remains invariant. This is the general result, correct? If you do classical mechanics, one of the strong points that we are proving it again and again, that if you add a constant to the Lagrangian, then the equations of motion doesn't change. Variational principle. But this is not true with Einstein's theory. If you add a constant to the Lagrangian, then you will not get the Einstein's equations of motion or Einstein's theory of, or Einstein's equation of gravity. You will get something different. That means that a symmetry which is existed in the matter world, that if you add a constant to the Lagrangian, then the equations of motion remain invariant. This is the property of the matter world, is not respected by gravity, right?
I think it was not for Hilbert himself. Is it right?
Not for Hilbert means?
Hilbert.
He was aware of it.
Yeah, he was aware of it. He was aware of it. Einstein aware of it. We are also aware of it. Right? The problem is with this root g. The problem is with this root g. Right? Once you put a constant here, that constant will be coupled with the root g and the equation of motion will change when you vary this. So you may see that there is no problem. Maybe gravitation doesn't follow the symmetry obeyed by the matter world. Or you can take the other stand that this is a very good principle. I am verifying again and again in the matter world. So I do want a Lagrangian which, adding upon with a constant, my equations of motion remains invariant. That is not obeyed by Einstein's theory. You can take it as a drawback, right? Second thing, the celebrated discovery of Hawking, 1970, right? The discovery is black holes will radiate. It is a very profound discovery. Why it is profound? Because we know that black holes are something which doesn't emit anything, right? If something is going into the black hole, it will last forever. So that is a thing which is violating the thermodynamics, right? If something is going into the black hole, the entropy will lost. That will violate the law of entropy. right? In order to balance the entropy, black holes must radiate. That is what he proved in a semi-classical way. Now the problem is, when you are saying that the black hole is radiating, it is a highly gravitating system, obeying the gravitational law, but when it is radiating, it is behaving like a thermal object, right? So you can ask the simple question, how a highly gravitating system will suddenly become a thermal object, right? And that question was again taken up by Hawking, and he analyzed the problem, and he surprisingly found that on the surface of black holes, Einstein's equations of gravity rebirth, or say take the form of a thermodynamic law. This is quite surprising. You have Einstein's equation of gravity and you project it or use it to describe the black hole surface, suddenly it will become the form of first law of thermodynamics, right? This is very surprising, right? Law of gravity is a geometric law, geometry of the space-time, but it attained the form of a thermodynamic law on the surface of a black hole. So he postulated, or he opined that this may be a very peculiar property of the black hole. On the surface of black holes, Einstein's equations take the form of a thermodynamic principle. We don't know the reason, right? So he thought that it may be a peculiar property of the black hole. But the point is that later on, it was proved that by Ted Jacobson in 1995 that it need not need black holes for the Einstein's equations to attain the form of a thermodynamic law. If you, for any general situation, what is known as a Rindler horizon, you can simply take, and if somebody is accelerating, suppose you are accelerating, then there is, you have a limitation of your view, right? That limitation we called as the horizon. So for an accelerating observer, there is a horizon, that is the limit beyond which he cannot access. And for that, it is not a black hole, An accelerating observer have a horizon, and in that horizon also, or the horizon of an accelerating observer, Einstein's equation will take the form of a thermodynamic identity. So it is not a peculiar property of black holes, but ordinary horizons feel by an accelerating observer. In such horizons also, gravity will take the form of a thermodynamic identity. In 2002, Tanu Padmanabhan have shown that he extended Jacobson result that in any spherically symmetric spacetime, need not be black holes, need not be horizons, Rindler horizons. In any spherically symmetric horizon or even spherically symmetric space-time, Einstein's equations of gravity take the form of a thermodynamic identity, right? So first issue was speculated by, yes?
By that statement, thermodynamic identity,
First.
give an example.
TdS is equal to du plus b dv.
Oh, that
Yes,
that is
the very same law.
Yeah, the basic.
Yeah. You can rewrite Einstein's equation as a TdS is equal to TdS, first law. And it was a surprise. Initially it was thought that it is true only in the case of black holes. And every space-time.
All metrics.
Space-time.
Yeah.
Space-time.
Space-time is characterized by
Yes,
metrics.
that is true.
So it is a geometrical problem.
No, it's a thermal property.
I don't understand how temperature arises.
That is a question that we are asking. Like suddenly I see that the gravity is behave like a thermodynamic property. Yes, thermodynamic property, right? That is a surprise.
Temperature should come out.
So the question is how a geometrical theory, right, rebirth itself as a thermodynamic theory.
That is interesting.
So that means that there is a strong connection between gravity and thermodynamics, right? But there is no explanation in Einstein's theory for this. Einstein's theory doesn't have any explanation why gravity behaves like thermodynamics in space-time, right? So this needs an explanation, right? Now once you believe that there is a strong connection between gravity and thermodynamics, you know, thermodynamics means something related to thermal energy, right? Any thermal object must have a heat, it must have a temperature, right? It must have entropy. All these phenomena are belongs to a thermal systems. So if you are getting the result that gravity equations are nothing but thermodynamic identities, that means that gravity may be a thermal phenomenon, right? Thermal phenomenon of whom? Thermal property of the space-time, right? Then you can ask the very fundamental question, whether gravity is the curvature of space-time or gravity is the thermodynamics of space-time. Right? And this question can be answered in a full-fledged way provided you create a theory which exhibits gravity or which explains gravity as a thermodynamic phenomena. Also, it should satisfy the earlier drawbacks. Suppose you have a Lagrangian by which you can write down the gravity equations as the thermodynamic phenomenon. That Lagrangian should be invariant under the addition of a constant, right? Now before going into that, it is interesting to know that if gravity is the thermodynamics of space-time, then I know that space-time must be hot, space-time must have entropy, space-time must have temperature, right? So all these properties, say heat, temperature, entropy, these properties have a very special characteristics. And pardon?
Isn't there only a parallelism between these two theories? Actually, the temperature concept we have in thermodynamic systems may not be the same as what you are talking about in space-time.
We have only one idea of temperature, one idea for temperature in thermodynamics. And what we are telling that thermodynamics is space-time is thermodynamic in nature. So we don't need a separate idea for temperature.
Is it just a parallelism between these
There is.
theories?
It is not parallelism. We are understanding that space-time is thermal in nature, right? Thermal in nature, right? If it is thermal in nature, there must be some microscopic structures to carry heat, right? It is directly implying that, see, if a matter has to carry heat, we know that heat is associated with the random motion of the molecules or atoms. Without microscopic structures, a body cannot carry heat, right? So the direct or the first implication of the idea that space-time is hot is that space-time has got a microscopic structure. Unless it has got a microscopic structure, it cannot be thermodynamic, it cannot carry heat, right?
So there is some energy related to the space-time temperature, space-time.
Yes, perfectly right. Right? So the idea that which
ഗ്രാവിറ്റി ഒരു തെർമോഡൈനാമിക് സിസ്റ്റം ആണെന്ന് സാർ ഉദ്ദേശിക്കുന്നത്. ഗ്രാവിറ്റി എന്ന് പറയുന്നത് സ്പേസ് ടൈമിൻ്റെ ഒരു പ്രോപ്പർട്ടി മാത്രമാണ്. തെർമോഡൈനാമിക് സിസ്റ്റം എന്ന് പറയുന്നത് സാർ ഉദ്ദേശിക്കുന്നത് സ്പേസ് ടൈമാണ്.
No. It is the property of the space-time is thermodynamic, and I am claiming that gravity is the thermodynamics of space-time. It is curvature of the space-time only at the thermodynamic limit. I don't know whether you understand. There is something called a thermodynamic limit. N tends to infinity, V tends to infinity, N by V is a constant. Right? So I am telling that because space-time is thermodynamic or it is carrying heat, it must have a microscopic structure. What we can call it as say atoms of space-time. Right? So space means atoms of space-time. So what do you mean by temperature? Or what do you mean by heat? Heat means the random kinetic energy of the molecules associated with. Therefore, the space-time atoms has got random kinetic energy, that you can call it as the heat. What do you mean by temperature? Temperature is the average kinetic energy of these molecules. Correct? Average kinetic energy of the molecules. Right?
What is actually space? Space and time.
Space and time.
You define space.
Space, usual definition is that it is a background scaffold upon which dynamics of the bodies are taking place. This is the basic definition. Other than that, what do you need? Only by general theory of relativity we are giving it an ontological status. Right? That means the space-time and matter can interact with each other, and matter can produce curvature on the space-time. They will interact with each other. So it is as like matter or energy. It is also a physical entity. Right? It can carry heat, it can carry temperature, it can carry energy, it can carry momentum. What else? Right?
Space-time can move.
Huh?
That case, space-time can move.
Of course.
Space, inflation. Yeah, you can explain
Yes.
in one stroke.
So the thing is that can you restructure or rewrite gravitation as the thermodynamics of space-time? So when you write it as the thermodynamics of space-time, you must first of all have a clear idea about the microscopic structure of the space-time, right? And can you count the microscopic structures? Likewise, you saying that in 1 mole of a liquid you have Avogadro number of atoms. Can you do a similar kind of thing for the space-time? Right? In fact, this can be done. Right? See, at the microscopic level or at the quantum level, space-time has a dimension 2. That is proved. And if fundamental dimension of the space-time is 2, I can say that in a unit, in a centimeter area of space-time, I will have, if I take Planck length, the fundamental length, the Planck length as the size of a single atom of space-time, then you divide the area with the Planck square area, Planck area, you will get the number of atoms. That means 1 centimeter square can contain 10 to the power 66 atoms of space-time. See, 1 mole of a gas or liquid will consist of Avogadro number, that is 10 to the kinetic energy associated with the random motion. So at the world of atoms, there is no temperature, only kinetic energy. There is no pressure, only momentum. Pressure, temperature, heat energy is all your construct. They are existing in the macro world.
They are emerging properties.
Correct. That is what I want to tell you. These are emergent properties. Right? So gravity is not there in the world of space atoms. It is an emergent property. When you say it is emergent, it is not fundamental. Gravity is not fundamental, it is emergent. Do you believe me it or not? Gravity is emergent. It is not a fundamental property of the space-time. That's all. Right? Similarly, I am saying that at the world of space-time atoms, there is no gravity. Gravity is only existing at the macro level. at the thermodynamic limiting level. So it is a thermodynamic limit, you are calling it as the curvature. Right? There is no curvature in the world of atoms, atoms of space-time. So it is an emergent property. Likewise, you don't need a special quantum theory of gravity if this theory developed in its full-fledged form. Why? We don't have a quantum thermodynamics. I mean, thermodynamics itself is quantum, right? Unless you have microscopic structures, you cannot build up thermodynamics. So microscopic structure is there. The only thing is that you have to define proper distribution functions. In material world, we have Maxwell's distribution, Dirac distribution, like that, right? So you have to identify what is the correct distribution, right? What is the correct distribution of the space-time atoms. From that you can do statistical mechanics, and you can go over to the thermodynamics. That will be the usual curvature gravity as mentioned by Einstein, right? So if this theory is developed in its full-fledged form, that itself is the quantum theory of gravity, right? Because thermodynamics itself is quantum. We don't have a quantum thermodynamics. Instead, what we have is statistical thermodynamics. There you need what is the probability distributions or distribution function of the molecules or atoms, right? And this thing is in its baby stage.
Is there any connection with the gravitons?
No, graviton is the quantum of gravitational waves. Nothing connected with the space-time.
So this is Barnoul's conjecture, right?
It is not a conjecture. It is not. Then you should say that Einstein's theory is also a conjecture.
The conjecture, right? But it has a proof.
This is also proof.
What is the proof?
Now, space you can measure. If you have an adequate apparatus, you can go down to such a level. Now, that is not going to happen at least in the next 2 or 3 centuries. And the proof is that the theory you are developing is invariant under the addition of a constant into the Lagrangian. Right? I get a covariant theory, and moreover that theory is invariant when you add a constant to the Lagrangian. That one thing. Second thing is that cosmological constant problem. It is a profound problem. It is a theoretical problem. Long standing for many years, there was no solution, and this theory is correctly putting forward a solution for the cosmological constant and correctly predicting its value.
See, suppose this Barnoul's conjecture is correct, so there is no need of going for quantum theory gravity.
Yes.
Right?
Yes.